Hello, everyone. This video is about different types of acids and bases that we have different theories and different definitions and how they all work together. So Arrhenius theory is the theory that it says an acid is the one that produces H plus ion or hydrogen ions, and the base is the one that produces OH minus ions or hydroxide ions. So examples are Arrhenius acids are something like HNO3, H2SO4, NH4 plus, pretty much anything that has an H or H plus that can be donated is considered as an acid, or even some organic acid like CH3COOH. So here, this has one hydrogen to be donated. So this is an acid. H2SO4 has two H pluses to be donated. NH4 plus has an extra H plus that can be donated. So one of the H's can be donated. And then in the case of these organic acids, the H's connected to the carbon are not acidic. So those are not considered as acidic hydrogens. Only the H at the very end of the molecule is considered as the acidic hydrogen. So these are the examples of Arrhenius acids. And then for bases is pretty much any base that comes with an OH. So something like NaOH, KOH, or SrOH2. So as you can see, these all come with an OH minus, so therefore they're considered as bases. So this definition, basically the way it works is that if you remember from the 6 types of reaction, one of the types of the reactions were acid-base neutralization, in which we say acid plus base gives us salt and water. And that's exactly based on this definition, based on Arrhenius definition. So imagine if you have an acid like HNO3 and a base like NaOH, what happens between them is the acid will give away the H plus, the base will give away the OH minus, and together they will form the water. And then the salt they make together is Na and NO3. So NaNO3 would be the salt. So this is the first theory. The second one is the Bronsted Lowry theory. So based on this theory, it's not about H plus, we call H plus a proton. The reason we call it a proton is because if you look at H plus, it essentially, sorry, I should not put the chart over there. H plus, so H plus has 1 and 1 for atomic number and atomic mass. So this represents the number of protons, which is 1. And then atomic mass is the number of protons plus the number of neutrons. So as you can see, since the proton number is 1, then the neutron number would be 0 in this case. And also, because the charge is plus 1, that means the one electron has been lost too, so there's no electron as well. And that's why they refer to H plus as proton. So based on this definition, an acid is the one that gives away the proton, and then the base is the one that accepts the proton. So this definition goes together, so they always react together. So let's say, for instance, if I have an acid like HCN and I have a base like F minus, so H is the one that has the proton, so it can give away its proton to F minus that doesn't have the proton. So what happens between them, usually their reactions, by the way, is an equilibrium reaction, is that HCN gives the proton to F minus. So what will be left from HCN is CN minus after the proton is lost. And F minus is now gaining the proton, gaining the H plus. So the charge goes up by 1 and the product is HF. So this is how they react together. So the acid always gives away its proton to the base. So examples of the acids we can have are same as the ones above. Anything with the H can be an acid, a Bronsted Lowry acid. So for example, HNO3, again, can give away the H here. H2SO4 can give away one of the protons. NH4 plus, same thing, can give one of the protons. And then the organic acid, like acetic acid, can give away its proton as well. And then bases, generally speaking, the one good sign to know if you have a Bronsted Lowry base is to look at the charge. So a charge of negative usually indicates that you are dealing with a base. For example, if you have F minus, that tells us that we have a base. Cn minus is a base. CO3 2 minus is a base. I'm not saying all the time they're negative, but for most cases, the negative is a good indication that you're dealing with the Bronsted Lowry base. So we have some cases, I'm going to show you after this one. So CH3COO minus is a base, because at the end, you see the hydrogen is missing from the end, so it can't always receive that back. And then we have some neutral bases, which again, they usually come with N, So it's like NH3, for example. It's neutral. However, it can always receive another proton to become NH4 plus. So these are examples of bases. So let's do another example for Bronsted Lowry definition. Another one would be like, for example, the case of H2CO3 and CH3COO minus. So in this case, the acid is the one that has the H's available to be donated, the H pluses, and then the base is the organic acetate CH3COO minus, which is missing the hydrogen. So this would be the acid, and then this would be the base. So what happens is that the acid will give away its proton to the base. So the product would become HCO3 minus, and the base will receive that proton, so it will become CH3COOH. One thing to note is that H2CO3 has, we call it diproduct, meaning it has two protons, it has two hydrogens. However, just because it has two protons, it's not going to lose both of its protons. So based on the Bronsted Lowry definition, there's only one proton lost and gained at the same time. You can't lose both of them at the same time. And another note about this definition is that there's a terminology they use, which is conjugate pairs. So we want to talk about that right now. So based on that, let's say looking at the first example, so HCN we said was the acid, and then F minus was the base. But if you look at the other side, imagine the reverse reaction taking place. So if the reverse reaction like this direction takes place, basically in this case, HF would be the acid and CN minus would be the base. So what we call these is that we say HCN. If HCN is the acid, we say that CN minus is the conjugate base of that acid. Or for example, if F minus is the base, the HF on the other side is considered as the conjugate acid of that base. So conjugate pairs are always one proton away from each other. So if the acid is HCN, the base will have, conjugate base will have one proton less, so it would become CN minus and vice versa. So these conjugate pairs are always one proton away from each other. The acid always has one extra proton, the base has one less proton, basically. So same goes for the second example. So if I have H2CO3, if this is the acid and CH3COO minus is the base, now looking at the opposite direction, now this is the acid and this is the base. So we can say if this is the acid, this is going to be the conjugate base of that. Sometimes they ask you to pair them up, so this way you can show it. And then if CH3COO minus is the base, CH3COOH is the conjugate acid of that. And this way we're actually pairing them up, showing how they are related to each other in terms of conjugates. And then we go to the third definition, which is the Lewis theory. So based on this theory, an acid is the one that accepts a lone pair, and the base is the one that donates the lone pair. So based on this, all the Lewis bases should come with a lone pair. That's very important. Sometimes they have a charge of negative, sometimes they don't. So something like, for example, F minus is a good example of a Lewis base because it has basically four pairs of electrons, and even though it has four pairs, it only donates one of the pairs, but that's an example of a Lewis base. Something like NH3, for example, if you draw the Lewis structure of NH3, it has a lone pair on the end. If you draw H2O, for example, you will see on oxygen, there's two lone pairs. Again, only one of those pairs can be donated, but these are all examples of Lewis bases. As you can see, the lone pair is the most important thing. Sometimes they have a charge of negative as well. And then the Lewis acid is anything that has room, extra room for receiving that lone pair. So boron, if you remember from Lewis structures, boron is one of those elements that it's an exception to the Lewis structure. So it's actually happy with 6 electrons after bonding, or in cases it can have 8. So for example, something like BF3, BH3 that have boron, and then boron always has extra room for receiving electrons. Or something like H plus. H plus doesn't have any electrons, so it actually has room for receiving electrons as well. Or other than these examples, generally speaking, we can say the cations, especially the transition metal ions, for example, Fe2 plus, Fe3 plus, all of these guys can be considered as Lewis acids. So I'll show you an example of that too. So for example, let's say we have a structure like BF3. So if you show the Lewis structure, this is how it looks. And then B, right now it's actually happy the way it is with the Lewis structure because it was an exception for the octet rule and it could have only 6 electrons, not 8. By the way, I'm going to tag my other video over here that I talk about the exceptions of Lewis structures in case you want to know more about them. Otherwise, you can just remember that B is one of those cases that can always receive more than 6 to become 8. So it has an empty box over here, so there's room for more electrons coming in. Now imagine something like NH3 that has a lone pair. So what happens between them is that the NH3, because it has a lone pair on the central atom, it's considered as the Lewis base. And then BF3 has extra room for electrons coming in, so it's considered as the Lewis acid. And in this case, NH3 is going to share its lone pair with B. So eventually you're going to end up getting BF3 connected to NH3 with a covalent bond. So this type of bonding is actually considered as a dative bond. So dative bond, which is also a covalent bond, is a bond that it's formed between 2 atoms, but the way it's formed is that one of the atoms is bringing 2 electrons, the other atom is bringing nothing, but eventually they start sharing. So normal covalent bond is an atom bringing 1 electron, the other atom brings another electron, and then they start sharing. But in this case, as you can see, the Lewis space is the one that is giving 2 electrons, and boron is bringing nothing. So, but at the end, they start sharing them together. So you have a normal covalent bond. Like it looks like a normal covalent bond, but it's actually a dative bond. Okay, so that was it for this video. I hope you enjoyed it. Hope to see you in the next videos.